Hello, this is Jun Chen. I am going to present our work, Visual GPT, Data Efficient Adaptation of Pre-trained Language Models for Image Captioning. This work is done by Jun Chen, Kai and Mohammed El-Hosani from King Abdullah University of Science and Technology, Han Bo from Carnegie Mellon University, and Boyan Li from Nanyang Technological University. Data efficiency is an important issue for real-world applications of deep learning in many domains, and especially in multimodal machine learning, because it is very expensive to collect enough high-quality multimodal data for training. Take the generation of medical image reports as an example. This task requires many medical professionals to do the annotation, which costs a lot of money. For another example, vision language tasks in low-resource languages such as Urdu or Tamil lack of high-quality data annotation. Then how could we improve the data efficiency for the training of a multimodal neural network? A natural thought is to leverage large-scale pre-trained language models such as GPT-2, GPT-NeoX, and Megatron Turing. Benefiting from the availability of single-modal data without any human annotation, these models are trained on hundreds of billions of tokens and have acquired substantial linguistic knowledge in the process. However, a major challenge is to bridge the domain gap between the visual and textual modalities with limited data. We highlight the domain gap by comparing the word-level distributions of MS COCO, an image captioning dataset, and Wikitext2, a text-only dataset. The two distributions turn out to be very different. In Visual GPT, to bridge the modality domain gap efficiently, we introduce a self-resurrecting encoder-decoder retention that effectively balances the visual and linguistic knowledge. This is an overview of our Visual GPT model. Here, we show how we apply the self-resurrecting encoder-decoder retention in the decoder. We directly apply GPT-2 as a decoder and initialize the colored parts such as masked self-attention and feed-forward layers with the pre-trained weights. We insert the self-resurrecting encoder-decoder retention in the red region and randomly initialize them, and its core idea is to rely on our designed SRAU gates to balance the visual and linguistic inputs. In this slide, we compare ordinary complementary sigmoid gates and our SRAU. The ordinary complementary gates can output values that are very close to zero. In contrast, with the indicator functions, SRAU directly sets values less than the threshold tau to zero, thereby it introduces sparsity. As the gradient cannot backpropagate through zero gates, our SRAU prevents small gradients from disrupting pre-trained weights that capture linguistic knowledge. This property proves critical in effective utilization of pre-trained models. We evaluate our model on the low-resource version of COCO and conceptual caption dataset. We also evaluate it on a medical report generation dataset, which only has few thousands of image-text pairs. We can observe that Visual GPT always outperforms the other baselines such as AOA transformer and X transformer. Specifically, it outperforms the best baseline by 4.1 CIDR score on training 0.1% COCO data, 6.4 CIDR score on 0.5% COCO data, and 2.5 CIDR score on 1% COCO data. Similarly, we can also see the performance gain on conceptual caption dataset. This indicates the superiority of Visual GPT in low-resource multimodal data. On the medical report generation benchmark, we found that Visual GPT is also able to outperform many other strong baselines. For example, its CIDR score can reach 49.7, higher than previous best reported score by 15.4. Let's have some qualitative results. In the top example, Visual GPT can generate more plausible and precise captions. It produces a woman and a girl sitting at a table with a birthday cake. But the other models generate incomplete and incorrect captions under the low-resource training. Thanks for listening to this presentation. If you want to look into more details of our work, please refer to our paper.